Good morning. This is the last part of our review for reciprocating engines. In a piston engine, the valve timing is the precise timing of the opening and closing of the valves. In an internal combustion engine, those are usually poppet valves. In a steam engine, they are usually slide valves or piston valves. So these are the following occurrences: valve lead, lag, and overlap. Let's discuss the valve lead first. So as the piston moves down under power, at a point before it reaches BDC, the expanding gases above the piston are no longer doing significant work, and the piston is exerting less and less torque on the crankshaft. It is better to open the exhaust valve a little early and allow these gases to expand out of the exhaust port, helping to clear the way for a fresh charge of air. This is known as valve lead, or the opening of the valves earlier than usual. So again, valve lead occurs when intake valve opens before top dead center and exhaust valve opens before bottom dead center. Also, high revving of the engine has a longer lead or lag opening and closing period, and low revving engine has a shorter lead or lag opening and closing period. The valve lag. Valve lag is the number of degrees of a crankshaft rotation after a piston passes the top or bottom center of its stroke, at which the intake or the exhaust valve open or close. This delay or the valve lag enables the momentum of the mixture to add the weight of the charge, or the moment of outgoing exhaust gases to pull more exhaust from the cylinder. Therefore, valve lag helps to increase the volumetric efficiency. Valve overlap. As the engine cycles, there is a period when both the intake and exhaust valves are open at the same time. This timing is known as overlap. Think of this as the exhaust and intake cycles overlapping each other. The valves are timed so the intake valve opens slightly before the piston reaches the top dead center on the exhaust stroke. Likewise, the exhaust valve is timed to close just after the piston starts down on the intake stroke. So again, valve overlap occurs when the intake valve and the exhaust valve overlapping each other at the same time. The objective of the overlap is for the exhaust gas, which is already running down the exhaust pipe, to create an effect like a siphon and pull a fresh mixture into the combustion chamber. Otherwise, a small amount of burned gases would remain in the combustion chamber and dilute the incoming mixture on the intake stroke. This valve timing is a product of the cam's duration and separation of specs. Firing order. This represents the sequence in which the ignition event occurs in different cycles. Every engine is designed with a specific firing order to maintain balance and to reduce vibration. For radial engines, the firing order is 13524. By the way, this is for a 5-cylinder radial engine. For a 7-cylinder, it's 1357246. And for a 9-cylinder radial engine, it's 135792468. For the inline engine, it's 123 for a 3-cylinder inline engine and 1342 for a 4-cylinder inline engine. And 153624 for the 6-cylinder inline engine. For the V-type engine, that's 1342 for a 4-cylinder V-type engine. And 13726548 for an 8-cylinder V-type engine. Last is the opposed. For an opposed, the firing order is 1342 for a 4-cylinder or 135642 for the 6-cylinder opposed engine. Manifold pressure. Power output is controlled by the throttle and it is indicated in the manifold pressure gauge. The gauge measures the absolute pressure of the fuel-air mixture inside the intake manifold. An increase in the throttle setting draws in more fuel air that is flowing to the engine and the manifold pressure increases. It is also important to remember that a given RPM should not exceed its manifold pressure. Fuel-air ratio. For a rich mixture, the ratio is 8 parts of air is to 1 part of fuel. And then of course, the lean mixture, which is 20 is to 1. And the stoichiometric ratio, or the ideal ratio, which is 15 is to 1. Also, fuel-air mixture is controlled by the mixture knob or lever. Here are some fuel-related problems. Fuel tanks contain moisture that condenses when the outside air temperature cools. So, as a solution, empty the space inside the fuel tanks that contains moisture that condenses when the outside air temperature cools. Or, refill the fuel tanks to full levels at the end of each day. Well, condensation occurs when the outside air temperature cools. So this happens at night when the air is much cooler than the land. Another fuel-related problem is pre-ignition. This is caused by the premature burning of the residual hot spot in the cylinder, which is often created by a small carbon deposit on the spark plug. This is also caused by using a lower than prescribed octane rating. So this is pre-ignition. Detonation. Detonation is the uncontrolled explosive ignition of the fuel-air mixture within the cylinder's combustion chamber. Here are some causes of detonation. The use of lower fuel grade than that specified of the aircraft manufacturer. Operation of the engine with extremely high manifold pressures in conjunction with low RPM. Also, operation of the engine at high power settings with an excessively lean mixture. And last is maintaining an extended ground operations or steep climbs in which the cylinder cooling is required. How do we avoid detonation? So keep the cowl flaps open on the ground. Use proper grade of fuel as prescribed by the in the OEM. Use a rich fuel setting during takeoff and initial climb. And avoid high power and steep climbs. Usually, mixture is leaned when the density of the air is lesser or it gets thinner. Pilots would start leaning the mixture at 3,000 feet. So here are some benefits of a properly leaned mixture. It gives better engine performance With the right amount of fuel-air mixture, the engine will produce the right amount of torque needed for a propeller to be efficient during flight. And last is fuel efficiency. Leaning types. So there are two leaning types, which is the rich of peak and the lean of peak. The rich of peak has a slight reach of maximum power and it gives off better engine cooling, while the lean of peak has a slightly lean of maximum power and a better engine efficiency. Improperly leaned engines have a serious effect on an aircraft's operation. So let's take a look at the two conditions for improperly leaned engines. First is a mixture that is too lean. This will cause the engine to have higher temperatures, therefore having a lower engine output, and the engine will experience roughness and could cause detonation and pre-ignition. While for the mixture that is too rich, the engine will have a lower engine output, a higher fuel consumption, and possibly spark plug fouling. If an aircraft is not fuel injected, it is carburetor equipped. The carburetor is a component of the induction system where fuel and air is mixed before it enters the intake manifold. Because of this, it is susceptible to icing, which is also known as carb ice or carburetor ice. When fuel and air enters the carburetor, a low pressure area is created at the venturi and or the throttle valve. This causes a sudden drop to the temperature that could lead to icing conditions. So, here are some of the conditions in which icing may occur. Formation of temperature below 70 degrees Fahrenheit or 21 degrees Celsius, and a relative humidity that is above 80%. The detection of the carburetor ice is quite difficult. However, there are some indications in the aircraft. One is the engine's roughness in a fixed pitch propeller. And the second one is the reduced manifold pressure, but there is no indication in the reduction in RPM. Functions of the carburetor heat. First is that it preheats air. Therefore, it prevents the formation of the carburetor ice. And last is the hot air makes the mixture richer since the hot air is less dense. The carb heat is also important during aircraft operations. It helps to reduce the engine power. It is used below the green arc of the tachometer, which signifies the reduction of power. For the presence of ice, there will be a slight increase in the RPM after applying carb heat. And if there is no presence of ice, RPM will decrease and it will remain constant. Piston displacement. This is defined as the volume of air displaced by a piston as it moves from the bottom dead center to the top dead center. Piston displacement is referred to as Vt. This is determined by multiplying the area of the piston head by the piston stroke. While total piston displacement is the total volume displaced by all the pistons during one revolution of the crankshaft. It also equals the number of cylinders in the engine, multiplied by the piston displacement of one piston. So the greater the total piston displacement is, the greater is the maximum horsepower that an engine could develop. So this is also known as volume displacement. The formula for piston displacement is area times length or the stroke of the piston. However, area is determined with the formula pi r squared or pi d squared over 4. So by the way, r is equals to bore over 2. And also the total piston displacement. So total piston displacement is obtained with the formula area of the bore multiplied by the length of the stroke times the number of the cylinders. So if a bore is too large, fuel is wasted, and the intensity of the heat and the restricted flow of the heat may be so great that the cylinder may not be cooled properly. On the other hand, if a stroke is too large, there will be excessive dynamic stress, and too much angularity of the connecting rods will be the consequence. A square engine has its bore and stroke equal. It provides the best and efficient engine performance. So here you can see an illustration of the square engine. So the proportion of the bore and the stroke has an effect in the engine's efficiency. A larger bore may require more fuel, while a larger stroke will result to angularity of the connecting rod. Crank radius. Here are some points to remember. Crank radius is solved by using the formula R is equals to S over 2. And also the length of the connecting rod. So technically, L is equals to 4R. For a 4-stroke engine cycle, 1 cycle per minute or 1 CPM is equals to 2 revolutions per minute. Again, this is for the 4-stroke cycle engine. Engine power or horsepower is the maximum power that an engine can put out. It can be expressed in kilowatts or horsepower. The power output also depends on the size and design of the engine, but also on the speed at which it is running and the load or torque. So here are some ways on how to measure engine power. Indicated horsepower, brake horsepower, and friction horsepower. Indicated horsepower, or IHP, is the total power actually developed in an engine cylinders without reference to the friction losses within the engine. So to compute for IHP, the average effective pressure within the cylinders must also be known. This pressure is referred to as the mean effective pressure. IHP is equals to Planck over 33,000, wherein P is the indicated mean effective pressure, L is the length of the stroke, A is area of the piston head, N is the number of power strokes per minute of one cylinder or that is RPM divided by 2, and then K is the number of cylinders. Friction horsepower. This is power required to overcome the friction and energy losses This is referred to as friction horsepower or FHP. It is measured by driving an engine with a calibrated motor and measure power needed to turn the engine at a given speed. Brake horsepower. It is the actual amount of power delivered to the propeller shaft. One way to determine BHP is to subtract an engine's friction horsepower from its indicated horsepower. Ideally, brake horsepower is 85 to 90% of the IHP. The formula for IHP is BHP plus FHP. Mean effective pressure is the average pressure inside the cylinders of an internal combustion engine. It is based on some calculated and measured horsepower. It increases as manifold pressure increases. There are two types of mean effective pressure. The indicated mean effective pressure or IMEP, and brake mean effective pressure or BMEP or BMEP. IMEP is the mean effective pressure calculated with indicated power. This parameter does not take into account the efficiency of the engine, while the brake mean effective pressure is the mean effective pressure calculated from the dynamometer power. Brake mean effective pressure is a calculation of the engine cylinder pressure that would give the measured brake horsepower. Brake mean effective pressure is an indication of the engine's efficiency regardless of the capacity or engine speed. IMEP. This is derived from the indicated horsepower. It is computed with the formula BMEP takeoff over the mechanical efficiency. Brake mean effective pressure is computed with the formula BHP times 33,000 over L times A times N. Also, we can use the formula 792,000 over displacement times brake horsepower over RPM, or the formula K times BHP over RPM. So displacement is the engine displacement, and K is equals to 792,000 over displacement. Brake mean effective pressure at takeoff. So to compute for brake mean effective pressure at takeoff, formula is brake horsepower at takeoff multiplied by RPM at cruising all over brake horsepower at cruising multiplied by BMEP at cruising over RPM at takeoff. Engine efficiency. This is the ratio of the input energy to the output energy of the energy supplied to produce work and the actual energy being converted into work. Engine efficiency is measured in several ways. It tells you how reliable an engine is. It is measured through thermal efficiency, volume efficiency, and mechanical efficiency. Thermal efficiency is a ratio of the amount of heat energy converted to useful work to the amount of heat energy contained in the fuel used to support combustion. An example of this is two engines that produce the same amount of horsepower but consume different amounts of fuel. The engine using less fuel converts a greater portion of the available energy into useful work, and therefore has higher thermal efficiency. The measure of the inefficiencies experienced when converting the heat energy in fuel to work is also thermal efficiency. Thermal efficiency can be calculated using either brake or indicated horsepower. If BHP is used, the result is brake thermal efficiency. If IHP is used, the result is indicated thermal efficiency. Indicated thermal efficiency is solved with the formula ITE is equals to IHP over the weight of the fuel burned per minute times the heat value times 778. While brake thermal efficiency is computed with the formula BTE is equals to BHP times 33,000 all over the weight of the fuel burned per minute times the heat value multiplied by 778. Volumetric efficiency. This is the ratio of the volume of fuel in air an engine takes into its cylinders to the total piston displacement. Another example is that if an engine draws in a volume of fuel and air that is exactly equal to the engine's total piston displacement, volumetric efficiency would be 100%. VE of most normally aspirated engines is less than 100%. The reason for this is because bends, surface roughness, and obstructions inside the induction system slows the flow of air which in turn reduces the air pressure within the manifold. Some turbocharged engines compress air before it enters the cylinders and often have VE greater than 100%. Volumetric efficiency is equals to the volume of charge at atmospheric pressure over piston displacement. Here are some factors affecting volumetric efficiency. Part throttle operation, long small diameter intake pipes, induction systems with sharp bends, high carburetor air temperature, high cylinder head temperatures, incomplete scavenging, improper valve timing, and increase in altitude. Mechanical efficiency is the ratio of the BHP to IHP. This represents the percentage of power developed in cylinders that reaches the propeller shaft. Mechanical efficiency is computed with the formula output over input, or simply BHP over IHP. Factors affecting power, manifold pressure, detonation and pre-ignition, compression ratio, ignition timing, engine speed, specific fuel consumption, altitude, and fuel and air ratio. So that's it for our discussion in reciprocating engine. Tomorrow we will start the discussion with gas turbine engines. Thank you for listening to this recorded lecture.